Okay, so we're going to be doing integration by partial fraction decomposition. It's a special technique. It allows us to integrate some rational functions by expressing them as a sum of simpler fractions. Okay, so it's just another trick to get around integrals that were otherwise non-integrable. Okay, it's going to employ the reverse process of finding a common denominator, which is why it's called by partial fraction decomposition, okay, because you're decomposing a fraction with the opposite process of finding a common denominator. Okay, so let's look at an example. I want to do the integral of 5x minus 4 over the quantity 2x squared plus x minus 1. Okay, this is a rational function. Okay, remember that we cannot integrate a quotient, so I would try u sub on, well, first of all, I can't simplify it. I should mention that first. I cannot simplify this quotient, so I would try u sub, and if I picked anything for u, normally I would pick my denominator, and if I let u equal the denominator, and I try to take my du, it's going to be completely unproductive. My du would be a 4x plus 1, and that has nothing to do with anything in my problem. Okay, so completely unproductive. So let's get rid of that. Okay, so we need another trick to get around this. And the trick is going to be to, first of all, look at the denominator and realize that it can be factored. So first of all, factor the denominator, pause, and come back to me. Okay, so this is what the denominator factored should look like. And the benefit of that is that I see that my denominator's factors are linear terms, okay? And if I just had a simple linear function in my denominator instead of a polynomial function in my denominator, then I can do something with that. I can do a much simpler u sub. My du would just contain a coefficient instead of containing an x value. So what I want to do is I want to realize that this fraction came from something. It came from a sum of two other fractions with these linear denominators. I don't know what those fractions were, but that's going to be our job to find out. So I'm going to write this as the sum of a over x plus 1 plus b over 2x minus 1. Okay, and all I did was I took each of the denominators from here and I made it its own fraction. Okay, and I said I don't know what those coefficients, sorry, not the coefficients, but what the numerators, what those constant terms in the numerators would be that would have gotten me to this end result of 5x minus 4 over x plus 1 times 2x minus 1, but we're going to figure it out, okay? So we're breaking it up this way with these unknown numerators, and I'm going to actually go ahead and complete the process of a common denominator here to figure out what would be. Okay, so if we think about what finding a common denominator looks like, I would want to get this as my denominator, and I would have to multiply my a times whatever was missing. I would multiply this piece here by both numerator and denominator, top and bottom, by whatever was missing, and it's missing a 2x minus 1. So I'd multiply top and bottom by a 2x minus 1. Okay, and then my b for this side, I'm just going to write about the numerator right now, but my b on that side, I would multiply top and bottom by whatever's missing to get to this denominator, which would be x plus 1. Okay, so let me clean that up. Okay, so I have my a times my 2x minus 1 plus my b times x plus 1. The only thing I didn't say is that if that's the parts of my numerator, those are the components of my numerator, when I combine them, I'm going to get the numerator that I started with, which is my 5x. I lost a sign there, huh? It'll give me 5x minus 4. Okay, so now I'm going to do some algebra with this, and that's really all these problems are. It's a lot of algebra to get me to some calculus. Okay, so if I wanted to solve for a and b, and I'm going to go through a lot of steps in this initial problem that you don't really need to do on every problem, but if I'm going to solve for a and b, I'm going to start by distributing a and b to kind of clean this up a little bit, okay? And really, you guys could have done this in pre-calc or algebra 2 even, but there's never a need to do a partial fraction decomposition, so we're doing it here, but I don't want you guys to have a misconception that we're doing any calculus right now. We're just learning some new algebra skills, or possibly some old algebra skills. So pause the video, distribute through that a and that b for me, and come back to me. And we should have a times 2x is 2ax minus a plus bx plus b equals 5x minus 4. Okay, the next thing I'm going to do is I'm just going to group together my x terms and my constant terms. Okay, so if you need to pause, go ahead and pause it. Group together your x terms with your non-x terms on the left side of that equal sign. Okay, and now I'm going to consider these two terms as one item, and these two terms as a separate item. Okay, and in doing that, I'm going to factor out the common term from here, which, what do they have in common? They have an x in common. So I'm going to factor out my x, and I should have this. I'll have 2a plus b times x plus a negative a plus b equals 5x minus 4. Okay, and the advantage to that is now I can match things up. So this stuff here is a coefficient on my x. Well, it's got to match the coefficient on my x that I get at the end. Okay, and the constant term is over here, and that's going to have to match the constant term here. Okay, so what I can do from here is that I can get that 2a plus b has to equal 5, and that the constant term, the negative a plus b, the negative a plus b is my constant term, has to match my negative 4. Okay, and this gives me a cute little systems of equations that I could have solved in Algebra 2. Alright, so before I move on with this, I want to talk about what I actually need to show in this big hot mess of what I did. Normally, I will go right from this first step, okay, straight down to this step, okay, and the reason I can do that is that I see that I have a 2 times an a times an x. I can distribute that and factor out the x all in one step and realize that I have a 2ax, factor out the x, and then get down here to my 2a. I'm going to have a b times an x, bx, factor out the x, I get a plus a b. Okay, and then what are my constant terms? My constant terms are going to be when I multiply my a and my b times my constant. So I have an a times a negative 1, which gives me a negative a, and a b times a positive 1, which gives me a positive b. Okay, so really, idealistically, every time you do this, you should be able to jump from here to here without a problem. And then you just set the coefficient on x equal to the coefficient on x, and the constant term equal to the constant term. And then you get to go back to Algebra 1 or Algebra 2 when you get to solve systems of equations, and you get to solve it any way you want to solve it. You can solve it using substitution, you can solve it using elimination. I'm going to do a quick elimination on this. I'm going to subtract the second equation. Okay, and by doing that, I will have 2a minus negative a is 3a. My plus b minus b goes away. 5 minus negative 4 is 9. So now I have a to be 3. Okay, I could plug into either equation to figure out what b is. And I plugged into the second equation. So if negative a plus b equals negative 4, then negative 3 plus b equals negative 4, which makes b equal to negative 1. Okay, these problems are very algebra intensive, and I haven't even gotten to any calculus yet. All I've done is found the coefficients that belong on my integral up at the top. Okay, and now I'm going to rewrite that integral using the coefficients that I just found. So I'm going back to this integral up here, and I'm going to replace my a and my b with the a value and the b value that I just found. Okay, so when you pause, replace a and b with the constants that we found, and come back to me. And you should have this integral now, the integral of 3 over x plus 1 plus negative 1 over 2x minus 1 dx. Alright, now I'm going to integrate these in pieces. Technically, they both require u-substitutions. For this first part, again, it's a quotient, it's composite, can't be simplified, but the u-sub is pretty simple. I can let u equal the denominator there. Okay, so u would equal x plus 1, and du would just be a straight up dx, and we'd have a really cute little integral of the integral of 3 over u du, which is real simple. I just got 3 times the natural log of the absolute value of u, which if I plug back in, I get 3 times the natural log of the absolute value of x plus 1. Okay, so I just did a lot of algebra and a teensy bit of a cute little calculus integral, and that's half of it. And now I've got to take care of this other half of the integral. Okay, now most of the time these integrals are going to produce you with natural log answers when I integrate them. It's not always the case, but for the problems that we're going to look at that show up in the AP exam, it is the case. Most of the time the u-substitutions are inconsequential, but if there's ever a coefficient on the x, okay, it will make a difference. So I'm going to u-sub this again, or maybe you should do it and pause it and come back to me when you're done. But we'll do u-sub on this. Okay. Okay, our u's are going to be our denominator again. U is 2x minus 1 again, but this time du is 2dx, which is going to change my coefficient out front. Alright, so I'm going to have, when I do my substitution, I'm going to have a 1/2 times the integral of negative 1 over u du, which gives me, I will get negative 1/2 times the natural log of absolute value of u, and if I plug back in, for that part of the integral, I get negative 1/2 natural log of 2x minus 1. Okay, so a lot of crazy algebra, a little bit of integration, and then I put everything together and I come up with my final answer, which is, from here I have 3 natural log absolute value of x plus 1, from here I have minus 1/2 natural log absolute value of 2x minus 1, and I can't forget my constant of integration. Okay, so horribly long algebra problem, easy calculus problem. There is a shortcut, okay? The shortcut works for every problem that you'll see on the AP exam, okay? But it will not work for problems that do not show up, for textbook style Calc 2 questions that are on the AP. I'm sorry, that are not on the AP. So you need to know how to do this technique so that you can do more complicated problems in a college-style Calc 2 class, but for the AP test, there is a shortcut that I'm about to show you. Okay, so shortcut time. The shortcut is called Heavisides Cover Up, okay? And I'm going to do the same exact problem that we just did. Using the shortcut, it's going to take out all that algebra. I've seen this spelled on the internet a couple different ways. Apparently it was named after a guy whose last name was Heaviside or Hervisor or something like that, but it's called Heavisides Cover Up. It's completely valid. You can do this on the AP exam. You need to know the long technique because this Heavisides Cover-Up does not work for every partial fraction integration problem, but it does work for every partial fraction integration problem that's on the AP exam. So this is what we're going to do. I'm looking at the factored form of the denominator, okay, and I want to figure out what those numerators are when I break it up into the sum of two linear denominator fractions. Okay, what I'm going to do is I'm going to look at each piece of my denominator. So I'm going to start with the x plus 1, and I'm going to ask myself, where is this equal to 0? Okay, and this is going to equal 0 when x plus 1 equals 0 when x is negative 1. Okay, once I establish where it's equal to 0, I'm literally going to cover up that linear piece, the linear factor. And now I'm going to plug in this x equals negative 1 to whatever's left. So I'm plugging it into this stuff. So if I plug negative 1 into here, I get negative 9 over negative 3, which is a positive 3. So I take that, right, negative 9 over negative 3 gives me 3, and I'm going to take that number and I'm going to put it in the numerator over the term that I just covered up. Okay, and you should notice that's the same numerator that we got from the last problem. Okay, and now I'm going to do the other side. I want to know where this piece is equal to 0 now. Okay, so I'm looking at the linear factor in the denominator. I'm setting it equal to 0. So 2x minus 1 equals 0 when x equals 1/2. Okay, and now I'm literally going to cover up the piece that I just set equal to 0, and I'm going to plug 1/2 in for x everywhere else in the problem. So I'm going to plug in 1/2 for x in the remaining parts. So I'm going to get 5/2 minus 4 is negative 3/2, divided by 1/2 plus 1 is positive 3/2, which gives me negative 1. And I'm going to take that negative 1 and I'm going to put it in the numerator on that part of the fraction. Okay, and those are the same numerators that we got when we did it the long way. All right, so you're setting the linear factors in the denominator equal to 0. Whichever factor you just set equal to 0, you're literally covering up, and you're plugging that x value into for all the remaining x's, and that provides the numerator for the linear factor that you just covered. Okay, and then I would integrate this the way that I integrate. I'm not going to reintegrate it. We went through all the u-subs and found our answer, but this is how I would get my 3 natural log absolute value x plus 1 minus 1/2 natural log absolute value 2x minus 1 plus c. Okay, so there you go. See part 2 for additional examples.